Okay, so in this second video, I want to define R modules in a slightly different way, which is a bit more abstract, but also much shorter. So you saw before when I wrote down the definition, it was quite long, but if you use this more abstract approach, you can give a very compact definition of R modules. But before I can do that, I need to do a little bit of preparation. So that n and n prime be two abelian groups. So in the lecture of Stefan, we have seen introduction of category theory. So he introduced these sets of morphisms. So I want to look at the set of morphisms from M to M prime in the category of abelian groups. So let me write it in this way. M primed, like this. So he explained that you have these compositions laws on these home sets. But actually, for the category of abelian groups, this is quite a particular category. In this category, you also have a way to add morphisms of groups. So we can define actually on these home sets the structure of an abelian group. So definition: if F and G are elements in home, so I'm going to drop these up groups. So just leave that implicit. So if I take two morphisms of groups from M to M primed, so abelian groups, and then I define F plus G. So this is going to be a new element of this home set. So I have to give, so let's say it's a map from M to M primed, and it's going to send an element M in M to the sum of the two guys, like this. And now you have a proposition. Home M, M prime together with this addition is an abelian group. So I'm going to leave the proof as an exercise, but it's can be quite useful to try to do this exercise and then also see where it goes wrong if you remove this condition that the groups are abelian. And this is no longer a group. Okay, so in the category of abelian groups, the home sets between abelian groups are actually themselves, again, abelian groups. So in particular, if I take if M prime is M, then the endomorphisms of M, that's just the home from M to M primed, has two operations, namely the plus, just by specializing this blackboard here to the case where M primed is M. And M plus M to M. Right, so I can sum two endomorphisms just pointwise. And I also have this composition, which I have in any category. So if I have two morphisms from M to itself, I can compose them and get a new endomorphism. So actually, in the category of abelian groups, endomorphisms have two operations, and you can show very easily that the set and M together with plus and circle is a ring. It's not commutative usually, so maybe I give an example. Let's just take R equal to Q, or maybe R equal to Z, and M equal to Z squared. Then the endomorphisms of M, they are equal to 2 by 2 matrices, but where I have now coefficients in Z. Okay, so that's a non-commutative ring. So using this ring structure on the set of endomorphisms, I can give a second definition of R modules. So for that, I proved the following proposition, which states the following thing. So let R be a ring and M an abelian group. Then I say in the map, so the following map. So I start with a ring and abelian group. So I make the map coming from the set of all scalar products that I can define on N. So all maps S from R cross M to M, such that the triple M plus and S is an R module. So satisfies those axioms that I introduced in the previous video. So I can make a map from this to the set of ring morphisms from R to endomorphisms of M. So M is here a group, so maybe I put that there to clarify. So I make the map in the following way, namely if I have such an S in here, I send it to what? Well, I have to make a morphism of rings. So a morphism of rings from R to this is something that will send an element R in there to something. Well, what endomorphism of M shall I make? Well, I make the endomorphism that multiplies elements M in M on the left with R using my map S, right? So I do S of Rm. So now I have to count how many brackets. 2 brackets. So I make this map. So this is a bijection with inverse equal to what? Well, if I have a morphism of rings like this, let's go with rho. So rho is in that set. I send it to the scalar product that sends a pair R comma M to, well, what can I do? I can put my ring element in rho, right? And then rho of R is some endomorphism of M, which I can evaluate at M. So that's the map backwards. Okay? So element of this set. So that's the statement of the proposition. I'm going to leave the proof as an exercise. So there are several things to show. You have to show that for any such S, the map that I write down here is really a morphism of rings, and that it sends any ring element to really an endomorphism of M. And conversely, that if you start with a morphism of rings like this, the scalar product that I write down here by this formula is a scalar product in the sense that I defined. So once you have checked all these things, you now realize that actually there is a much easier way to define what R modules are, namely just using this right-hand side. Right, so you can now define an R module so maybe I say second definition. An R module is a pair M, rho consisting of an abelian group. M is an abelian group and rho is a morphism of rings. Rho coming from R and going to the endomorphism algebra of M. Like this. Okay, and so if you want to translate between the two notions, of course you just use this bijection, right? So if I give you a pair like this, you put it in the bijection that I wrote down, and then you get an R module in the previous sense. And if you had an R module in the previous sense, you can translate it using this bijection to an R module in this sense. Okay, so we get one corollary, and that is that any abelian group M is a Z module in a unique way. And what's the proof? Well, the proof is just, we know that Z is initial in the category of rings. So
I have a question.
Yeah.
So I think Stefan did not talk about initial and final objects. So maybe it's good to remind to say it too.
Okay, so then I explain what is an initial object. Okay, so the proof is to be continued. It's very short, but if you don't know what an initial object is, then you should maybe say that. Okay, so definition. Let's see the category. Right, so here I was about to apply it to the category of rings. You can do it for any category. So let C be a category. Then an initial object is a pair. Let's call it.
Why is it a pair? Just an object?
Oh, it's. Yeah. Okay. So it's an object. X in C, such that for any other object, let's call it Y in C, we have a unique morphism from X to Y. So maybe I say that the home set has precisely one element. Okay, so what you can show is that initial objects are unique up to unique isomorphism. Because, or instead of proof, proposition, because if I had two initial objects, well then I know that I have a map going from the one to the other and backwards, but then this backwards map has to be the identity, because
no, the composition.
The composition has to be the identity, yeah. So these initial objects, you may or you may not have them in a given category. So in the category of rings, it is Z. So maybe write this down. So, example. If C is rings, then Z is an initial object. Because if I because if I give you any ring R, how do I make a map from Z to R? Well, I know where 1 has to go, because that's an axiom. 1 has to go to 1, and then 1 plus 1 has to go to 1 plus 1, and so on. And minus 1, I know it has to go to the inverse of minus 1. And then I can also keep adding minus 1 many times. So I see it's completely uniquely determined. And if I take this as a definition, some kind of inductive definition, then I see I also always have such a map. So that's why in the category of rings, Z is an initial object. So now coming back to the corollary, I know that Z is an initial object. This thing is some ring, so I know that there exists some unique map from Z to the endomorphism algebra of M. So that gives M the unique structure of a Z module. Of course, the module structure that you get it's completely obvious, because what does it mean? If I have some element M in M and I want to multiply it with some scalar in Z, let's say it is 5. Well, what do? I write 5 as 1 plus 1 plus 1 5 times. I multiply with M, I use my distributive property. So I see that this has to be M plus M plus M 5 times, right? So that's how this Z module structure works. Okay, so that's the end.